All right. Welcome everyone back. Okay, so this is a final talk of the day. It's my pleasure to introduce Aditi Raghunathan, who is currently a professor at CMU. Before CMU, she was at Stanford, and I remember like we overlapped a bit, and I remember one of the works on safety guarantees was not robustness guarantees that was so popular that got stuck with me. Like whenever I think about now, whenever I see a paper about guarantees, I only think about you. Yeah, Aditi also won Best Thesis Award at Stanford. That already tells you something about her. She's also Smith's Fellow. So thank you, Aditi.
Thanks, Siva, for that kind introduction, and thanks for inviting me. I was a little scared when he started saying some Stanford anecdote because I didn't know what was, coming from our time together. I also didn't know that was the work I was invited for, so this, may not scratch that itch. But anyway, so thanks for sticking around till the end of the day. And some of the talks earlier today were extremely comprehensive and covered a lot of things that I was initially thinking about. So I changed up my talk a little bit. So this is a last-minute attempt, but it's stuff that I've been thinking about and I'm excited to discuss. The field is moving so fast that something from 3 years ago feels like a really long time ago. And when I was on the job market, and a lot of the big conversations around the open questions in machine learning were around distribution shifts, reliability, adversarial examples, and so on. So kind of had these slides where we had all these motivating examples as well as wonderful benchmarks people had to show that if we train on certain distributions but actually try to deploy them in different settings, things break, and we were really interested in developing new algorithms to do that. But over time, this kind of got subsumed by just training on more and more data. And so there was this sense that maybe we just train on everything, then there's no really notion of distribution shifts. And we did as a community, did a really good job of figuring out how to scale up learning from unsupervised data sets or self-supervision and so on, that it actually became feasible to learn from virtually unlimited data. And so, So I'm going to try to argue that all of these core challenges of distribution shifts that we hadn't solved before had not actually kind of gone away by the fact that we are training on more and more data. They just take a slightly different form. So if you look at our current safety pipeline, I think this is kind of how most people are doing it, is we pre-train a model on as much data as we can. We really try to build an enormous model that has seen and digested large amounts of data. And some of that is going to be harmful, like the model might have certain harmful capabilities. And there's a hope that we can try to control or align these models post hoc by doing some kind of fine-tuning. So a lot of the approaches that people think about today are basically this kind of what it boils down to is we take our largest pre-trained models and try to do some kind of fine-tuning to make them safe. And of course, there are a lot of details on what exactly is the fine-tuning procedure, what's the data, and so on. But we can think of this abstraction. And when we talk about training on more and more data, I think we can do a really good job of scaling up the pre-training data because fundamentally it is not curated in some sense, and we can learn in this self-supervised manner, so that really makes it easy to scale up the pre-training data. And that is the trend. Like, we are trying to train on more and more data. And if you're worried about running out of data, don't worry. There's synthetic data that you can add. And so people are really trying to scale this up. But there is still a problem that when we try to align or control these models in some way, we are, again, somewhat fundamentally limited in that there now needs to be some kind of careful supervision of, like, people call it red teaming or so on. Like, how do we decide or collect data or examples for what is exactly harmful and what is helpful, what is harmless, and so on. And so I think that kind of bottlenecks that we can't just really scale this up. And our safety fine-tuning might still end up being unlimited limited data. And so the questions of distribution shift kind of shift to thinking about like how robust is our fine-tuning or alignment process? Does that actually generalize beyond the kind of data that you're trying to fine-tune these models on? Even approaches that involve, applying some kind of guardrails to these models also rely, like, maybe you have some prompts or instructions. They also really rely on fine-tuning a model to obey instructions in the first place. So all of these approaches and safety kind of fundamentally depend on us believing that we can fine-tune or align these models somehow. And I think a really core challenge in AI safety that is maybe shared across all of these different approaches that we can try is that when we do some kind of post-training, like it might not be robust. Because we can't post-train on, we end up post-training on limited data, and we're trying to control a model that was trained on much, much more data. So this is a work from a year and a half ago at this point, but this got me interested in thinking about distribution shifts and safety, and was very, like kind of a concrete example to me. I think it kind of came up in the earlier talks as well, where if you look at some of these back in the day, like a year and a half ago, it was actually easy to jailbreak models by exploiting the fact that a lot of their fine-tuning data was predominantly in English. And we, in fact, came across this not really through safety, but through looking at another behavior, where we were just trying to look at what happens to models before and after instruction tuning. And so if you look at this instruction tuned model, like there was this general growing consensus that these models are not good at in-context learning. And we do observe that that is true. So if we give a bunch of examples and we want the model to do in-context learning, it seems like the model is more biased towards answering the questions or following instructions. But this ability was actually, this behavior was only in English. If you kind of prompted it in a different language, like here, you actually see that the model does in context learning when prompted in a different language. So this was a very concrete example to me how this was an issue of generalization, in that when we trained the model to follow instructions predominantly on English data, the model does not generalize to actually following those instructions on other languages. And it's not an ability issue, because the model is able to comprehend different languages. It's just that our instruction tuning procedure did not generalize. And this could be a good or a bad thing. In some sense, it means that some abilities of these models are not necessarily forgotten and could be gotten back. But you can see that from a safety perspective, this got us concerned that it's not that trivial to actually generalize from in this, like when we do safety fine-tuning, even if we used a really powerful model that a priori seemed like it was really good at comprehending multiple languages and so on. And so we went ahead and tried this out, and this is, I think 3.5, I forget, but some model a year and a half ago, the state-of-the-art model, and we did see what we expect, which is you prompted in English, things are, the model is not jailbroken, it's really been trained to do this. But if you prompted in some other minority language, I believe this is Malayalam, and the model actually starts outputting code and really gives you the, answers the question you asked, which was harmful. And again, this was not that the model did not have multilingual abilities. It was able to execute those instructions, and it's really an issue that the safety training did not generalize. Some of these issues have kind of gone away. Like none of the latest models can be jailbroken in this way. And I'll get to this towards the end too, but I think a lot of it has to do with the safety data being more carefully collected and multilingual, rather than the base model itself somehow being better at generalizing. And this was sort of a question that kind of came up, and I'll try to address that broad question in a bit. There are so many examples of things being brittle, but one thing that I've been thinking about, and I think is particularly hard, or where our current approaches might break, is when people are trying to build agents using these LLM backbones, because now there's just such a vast diversity in how you can use this model and what inputs go into these models, that it might actually be extremely hard to generalize. And this is an interesting paper which saw that you can just give the same question to a chatbot, but and the model will refuse. But if if you give it in this agent environment and with like access to emails or to a browser agent and so on, it's actually going to execute the task. And I think this is another instance where there's just generalization issue, because a lot of these models were probably not red teamed to actually handle specific browser agents or specific kind of inputs that go into these LLMs. And so this is one thing that we've been thinking about, but there are plenty of other examples, and a lot of the talks earlier today had many of those examples. So I'm going to talk about kind of this robust post-training notion where we are starting with a pre-trained model, and we have limited data that we're trying to adapt or teach the model to be safe, or maybe even other downstream capabilities. But how do we actually make this robust? And going back to like research from 3 years ago, it's not like we really solved this problem even when back then, and even in much simpler, maybe arguably sort of constrained settings, it was hard to get robustness. But I think what's interesting about this post-training setting is that we are not starting from scratch. We're actually starting from an extremely rich starting point. And I think that was kind of the intuition underlying some of the questions or discussion earlier today over, as models get more capable, are they able to robustly extrapolate or generalize? Because they are more capable in some way. So we are starting with a rich starting point. And I think this kind of changes both the algorithms and what's possible. And even if we just look at any kind of fine tuning without any tricks involved, like we take a pre-trained model and see what does after post-training or fine tuning, it does end up generalizing much more than better than training from scratch. So we are able to see those benefits, but maybe there's also a lot more we can do because we have a much richer starting point that could ideally enable us to be more robust, and even though robustness in general is challenging. So even though we have an extremely rich starting point, I'm going to argue and maybe show some examples about why it feels to me like we do not know how to effectively use our pre-trained models, especially with the current machinery of fine-tuning, or I'm going to use post-training and fine-tuning kind of interchangeably, because it's really the same process where you collect a bunch of data and then you update the models by doing gradient descent on the objective. And I'm going to hopefully convince you that a lot of what we're doing is not very effective. And there are probably better ways to post-train and use these pre-trained models that hopefully we can all think about. In particular, I think one way that I think about this is we want to preserve the broad understanding that these pre-trained models have that would enable them to generalize or extrapolate better from limited post-training data. And so that's kind of the lens I'm going to use when I try to analyze or show results in analyzing our current post-training methods. And this might be a little bit confusing because in some cases, we do want to robustly unlearn harmful knowledge. But I think that also requires preserving the broader understanding from the model, because we somehow rely on the model to understand like what it means to actually robustly unlearn. So even when I'm talking about like robust removal of harmful knowledge stuff, I'm still talking about preserving the broad understanding that we have from a pre-trained model that has been trained on a lot of data. So I've been thinking about in my group, thinking about new algorithms and data curation. But in particular, in today's talk, I'm going to focus on the interplay between pre-training and post-training, because I think that's one case where I feel like our current trends or our current trajectory for how we pre-train models might actually be suboptimal, and we might need to kind of rethink how we do that. Okay, so the kind of one-line takeaway is, at least with our current pipelines, if we look at how we are improving pre-training by training on more and more data, that actually hinders our post-training outcomes. So if we take a model that has been pre-trained longer, but look at how easy is it to adapt or control or fine-tune these models, you'll find that a model that was pre-trained longer can actually be worse. And even in the most kind of innocuous sense of improving pre-training, where we train on more data. So like no one's gonna believe you if you say that training on more data is a bad thing. But like one example where we found that this is actually true is if we keep increasing the amount of pre-training data, we see that we're actually making everything worse in terms of the final post-training outcomes in certain settings. And I mean, it should be surprising or skeptical. And if that's true, like you kind of, yeah, like I was skeptical too. And so I'll show you and try to explain why that can happen. So this is work with students at CMU and a broader collaboration across Princeton and Stanford. And this is a paper we put out about a week ago about how overtrained language models are harder to fine-tune. This is a slide I took from my students. Like I haven't been in this job for too long, but I have still not made llama cartoons on my own slides. But I guess this is the first time. So we look at like in general, like the trend nowadays is to train on more and more data, especially because people are care about inference time efficiency. The trend has been to fix a model size, but just train on more data. And that seems to improve performance, at least in some senses, and I'll argue, but not in other senses. So llama trees, and just to clarify, this is much beyond sort of compute optimality, because you're taking a really small model and training on a lot of data with the hope that we get a powerful small model that can be used efficiently at inference time. And especially with the growing trends towards using test time compute and trying to sample multiple times and so on, it kind of really is the trend to try to get smaller and smaller models, but you would be pre-training on more data. So we ran this experiment where we looked at ALMO 1B intermediate checkpoints that were released. And so as we take various degrees of pre-training and look at how does the model work, we try to do this analysis of how do various pre-trained models actually behave after doing some kind of fine-tuning or post-training. So the first thing to observe is that, well, if we just measure performance on the pre-trained model itself, we do see what we expect, which is that the performance tends to go up, and this is queried in few short settings. So we see that the pre-trained model does improve, which is what you would expect because it has been trained on more data. So in some sense, the idea that more data is good is true, like the pre-trained model is improving. But what we find interestingly is when we measure various aspects of the downstream performance, but in this case, we looked at, we post-trained on Alpaca and other instruction tuning data sets, and we saw similar trends, where if we measure performance on various other benchmarks, we see that the performance improves, but at some point when it's trained for too much, we actually start seeing worse performance. So this model that was 3 trillion tokens actually does kind of worse than a model that was around 2.3 trillion tokens. So this was somewhat surprising because there was a growing consensus that a better pre-trained model is just better in every way, and one way to get better pre-trained models is to train on more data. But we find that that's actually not true, because if you look at how people actually use these models, at the end of the day, they are going to do some kind of in this case, we're not specifically talking about safety alignment, but that's also one part of the pipeline where we're trying to control or change these models in some way. And what we find is, at least after this kind of adaptation, the outcomes are not necessarily that more pre-training data is better. Yes.
Is this re-optimizing hyperparameters at different points on the curve?
Yes. Yes. But what's different is that the benchmarks that is evaluated on are different from what it was fine-tuned on. So we measure the hyperparameters on the Alpaca eval or some instruction tuning evaluation. That's a bit different from these benchmarks. But each of these points are tuned separately. Yes. Yes.
So how much do you understand this phenomenon, or how robust is this? Because obviously, this is one example, but on the other side of the coin, right? We now have several years of models of the same size when they're instruction tuned being way, way better for users than the previous.
Yes. Yes. I'll get into that. Yes. Yes. So quick answers. It depends on the model size, amount of data, and the distributions, and I'll try to shed some insight to all of those axes. Yes.
So the chinchilla scaling laws and these things, they state as you increase the data, it goes up. Mm-hmm. It's not There's a optimum point where there's for certain compute, this is the best data.
Yes.
But then the scaling law actually says it keeps going up. So what is the difference between that scaling law and what you have here?
Yeah, so here we're not dealing with compute optimality. So in some sense, all of these models are like this Olmo model is like not compute optimal because it's trained on much more tokens. So this is taking into account because at inference, like it's better to use a small model. So all of these models are like trained way past the chinchilla optimality. So that's one thing. And the other thing is like all of those scaling laws only look at the pre-training laws. And so if we just look at the pre-training performance, so this is zero-shot or few-shot performance and benchmarks, but we can also just measure perplexity on some reasonable like C4 or something. I'll go into that. So in all of those cases, the more data just does help. So the model does improve in that sense. But none of the scaling laws have actually looked at what happens if you take these models and then adapt them in some way. So these models are like, they correspond to this checkpoint. For example, it's like, it's here. You take the model and then you do some kind of instruction tuning. Yes.
Are like economic properties. They don't tell us anything about the model.
Yes, exactly.
So are you saying that it starts going down after that, or it's like if you're 10 times past that, it starts like?
This is, yeah, no, it would be like several, like it would be like maybe like 10 to 50 times past that. Then, so we still haven't hit the point where the pre-training loss goes down. So it's not like an overfitting in that traditional sense that the model doesn't have enough capacity. Like whatever you're optimizing on, it is still getting better. But the issue is that what you're optimizing on is not exactly what you want downstream eventually. And that mismatch starts kind of giving you problems beyond a certain point. Yes.
I'm curious if you scale the amount of post-train instruction tuning to the tokens, do you get a linear, or do you get this budget pattern?
Yeah, we didn't try. Okay, so we didn't run this experiment, but other people have looked at just scaling laws purely in terms of, so the x-axis here would be post-training tokens, and you will see that it generally improves. So you only see this kind of like mismatch. You only see this issue when you're scaling pre-training tokens, but you're doing something else with the model.
I mean, you could say it's just a mismatch that pre-training tokens swapping out post-training. The post-training token.
Yeah, I'll get into kind of one way of thinking about this, and that will clarify. It's a bit related. Yeah. Yes.
So over pre-training is not recommended.
So
Over pre-training is not recommended.
That's sort of my claim, yes, but people currently do overtraining.
So how to measure that? I should stop now pre-training.
Yes, I'll get into a little bit more analysis that might make that clearer. Yes. Yeah, so these benchmarks were like kind of held out in some sense. So like it was not exactly the benchmarks that the model was post-trained on. We also look at what happens on the benchmark that you were hyperparameter tuned on and so on. So even there, we see a similar trend where the model improves to a point, but then actually starts getting worse. So the response quality and exactly what we cared about, like if we measure as well, we see this trend that taking a model that was too overtrained is actually worse. So we call this catastrophic overtraining, where at some point you will hit a threshold where more pre-training, and I guess this goes to Sasha's question, the threshold is different from the chinchilla optimality threshold. It's a different threshold beyond which more pre-training is not actually better in terms of the final performance. And we could see degradation along two axes. One is just the in-distribution performance, like whatever you fine tune on, like on a held out set from the same distribution, like how does it work? And we see a bigger sort of degradation in this out of distribution sense, where we are fine tuning on some tasks, but we're measuring the general capability of model on other sort of related things that are slightly different. And there we see that the robustness or this forgetting aspect is more exaggerated. So both of them tend to degrade, but in general, the robustness degrades like sooner than the adaptation itself. And they're not necessarily orthogonal, because in some sense, why we see better performance with pre-training is because you're able to retain that pre-trained knowledge in some way when you fine-tune. And so they both related to whether we are able to preserve the pre-trained knowledge. Yes. 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 Same data set.
Have you ever tried varying, like how you do the post-training to adapt to?
Yeah, so in this case, we're just doing standard fine-tuning. We change the learning rate, and we tune the learning rate on like an held-out evaluation set. The same thing. Fixed for everything, yeah. Yes.
When you get this decrease in performance, where are you in terms of number of training buffers?
These are all single epoch. It's just like more tokens. Yeah. So there's no overfitting in that traditional sense. Yeah. Yes.
What tasks used for post-training, like experiment classification or generations data? What type of tasks used for post?
Yeah, so we do instruction tuning on a bunch of standard data sets like Tulu and so on, and the benchmarks are standard like knowledge data like MMLU and things like that. Yeah. Yes.
Does more post-training data help you recover from the drop, at least for in distribution?
Yes, I'll get to that. I mean, in some cases, yes, but not always. So this is actually could be something fundamental. Okay, great. So yeah, we also see this in another sort of setting of fine-tuning. So these are all still on these almost real-world large-scale models, and we're trying to use these models for for multimodal fine-tuning. So if you take these language models and try to make them process in images as well, and we see sort of similar trends where in some cases training for longer can actually, like for example here, like actually makes it kind of worse at other tasks. Okay, so and I guess a lot of people were already asking questions on this, and so we dug into this a bit more in like a smaller scale control setting where we can actually vary a lot of things to understand when and why do we see this phenomenon of catastrophic overtraining. So one thing is there's one confounding factor in that in our previous experiments, we took publicly released checkpoints where because of their learning rate schedule, like every checkpoint was kind of saw a different final learning rate. And so that could have been that can potentially be an exacerbation effect where it's just like things that were, that we took at the end just were trained with a really low learning rate and somehow that affects things. So to control for that, we trained our own small models where every checkpoint is kind of sees the same learning rate schedule. And we train much smaller models, of course. We pre-train on C4 high quality web data. So we're ensuring that across, as we vary the tokens, the quality of the pre-training data remains the same. And we fine tune on various language modeling tasks. So we looked at some canonical language modeling tasks. And because these are small scale models, some of the evaluation signal and benchmarks can be a little weak. So we went to the source that we cared about, which is we're trying to see how much does the model retain its pre-trained information. And so we measured perplexity on the C4 web data itself as a proxy for, is the model able to retain its vast pre-training, or does it end up forgetting things as we fine tune, and how does the trend vary? So across like a bunch of different standard data sets, we plotted what this looks like. And so since it's the perplexity now, lower is better. So when we see overtraining, you're going to see kind of a U curve where it improves to some extent, but beyond a point, it actually gets worse. So again, we don't see it on all data sets, and I'll explain a little bit why. But we see more data sets, but this is just a subset where we end up seeing this kind of catastrophic overtraining. And we have like clear signal that it's not really just the learning rate issue because everything is controlled. The only thing that varies across these checkpoints is the number of pre-training tokens. And since so I guess the mental picture that we were trying to think about is one way to view what's happening when we fine tune is some modification or some change to the model. And we want to see how much does this change or perturbation affect the overall properties of the model. And a lot of our current fine tuning is not specifically targeted, and we just kind of pass gradients across the entire model. So we can think of what's happening is a lot of things are kind of, maybe changing in various weights, and that affects how much the model retains its pre-trained knowledge. So just as a warm-up, we try to run the same experiments, like the same pre-trained models, but try to look at their behavior. If we just added some noise to each of these weights, how does that change the degradation in these models? So we measure the drop in perplexity of each of these checkpoints as we add some noise to the model weights. So this is a very loose approximation of fine-tuning, of course, but this gives us some insight into what could be happening. And now we see these really clean trends where as we, so this is increasing perturbation. So of course, as we increase the perturbation, the drop is higher. But also, as we increase the number of pre-training tokens, we see sort of a monotonic increase in this drop. So just the, I'm sorry?
The units seen here, 10 to the 1, 2.
Oh, the pre-training tokens? Yeah, there's like, this is multiplied by, I forget. I think these are millions of tokens, millions of tokens, yes. Yes. So these are trained on like quite a few tokens, which is so they're like pre-trained on very overtrained. Okay, so we see kind of these clean trends where the absolute degradation keeps increasing as we train the models more. And of course, it depends on the magnitude. The more magnitude you add, like the more you lose. But we kind of see this trend. So models seem to become more brittle, so they cannot stand changes in their weights without dropping their perplexity or without losing their pre-trained knowledge as we train them longer. So if we extend pre-training, models end up becoming more brittle. But also, as we train longer, the absolute, sorry, yes.
So maybe it's answered by
okay.
There's a literature on the sensitivity of models to, say, quantization. There's like power laws relating that to
yes.
It seems to be
yes.
What, I don't understand the connection between that and fine-tuning exactly.
Yeah, it's actually like, so we did the scaling laws of precision like in collaboration with my group, and that's what somewhat motivated this mental picture as well. The connection to fine-tuning, and I'll speak about that a little bit later. But I think we can think of it as some kind of a perturbation to the model. So like we are pushing it in some direction, but we don't have a way to do that that's very targeted right now. And so in the process, we are kind of perturbing everything in the model. And so we can measure what is the effect of that kind of perturbation. And so I think like that's the way I view this, is that we don't have good ways of fine-tuning these models that are, that don't change a lot of things. And given that, like, what does that mean for how we update these models?
The fine-tuning is some other loss that's like somewhat unrelated, and so it's a weird thing to be doing to the model, and weird things will break the model more if it's.
That's kind of one way to think of it. Yes.
The first graph is not really surprising. As we train, we go deeper into shallower basins.
Yes.
Second derivatives will be larger, and then of course now you're going to be more sensitive to perturbations.
Yes, I think that's exactly.
Interpretability has to have that property.
Yes, so I guess it's not that surprising, and maybe the surprising part is that we see similar trends with fine-tuning, and like maybe kind of related to the previous question. I guess what it tells us is the way we align or fine-tune these models in current approaches, where we just update the model with gradient descent, without constraining it in any like meaningful way, is actually, you can think of it as adding noise. And so like if we actually train for longer and we are in these basins, like we are losing control of sort of what happens. Yes.
What's the variance for how many samples did you check?
We ran like at least like 5 to 10 runs, and the variance is very small for this particular experiment. For the fine-tuning experiments, the variance is a little bit higher, but for these ones, the variance is quite low. I guess there are no error bars here, but on the fine-tuning plots, like I have the error bars, and they are You can see, so like, oh, sorry, it's not super visible, but like that's kind of the bias thing. Yeah. Yeah, so as we pre-train more, like so there are two competing factors here where the models are learning more, but then they're also becoming more brittle. And so they like you will eventually get this U kind of trend where the brittleness will overtake whatever you actually improve by seeing more tokens, like the improvement in knowledge. And so we kind of see this trend where beyond a point, it kind of may not be a good idea to pre-train if we are going to modify this model in some way downstream. Yeah, so this is kind of the same schematic where in general, our base model or our pre-trained model does keep improving, but then they also get more sensitive. So if we put them together, we kind of get this trend where, and I don't know where we kind of are with respect to various tasks, and I'll talk about that a little bit. But in general, we should expect that if we keep training these models longer, more and more data, we are going to have a harder time with updating them. Yeah.
About forgetting the fine-tuning results. And now we're talking about forgetting the pre-training results.
Yeah, I'm always talking about forgetting the pre-training. And it's a little bit tricky because sometimes what we want during the fine-tuning process is to forget something. But I think to understand what to meaningfully forget, it actually requires pre-trained knowledge. And so if we, for example, lose a mapping between various languages in some deep way, then saying something is harmful in one language doesn't automatically generalize to another language.
Got it.
Yes.
Do you experiment with the number of parameters as well?
Yeah, so all of these are fixed model size. And if we increase the model size for the same, so if we look at this threshold here, this threshold will shift to the right if we increase the model size. So you can train on more tokens until you start seeing this inflection. So I don't know if token to parameter ratio is the right quantity, but it seems to depend on both of these. And yeah, so the bigger model can tolerate more training. And so all of our experiments are on the 1B model. And when we actually tried the 7B model, which was trained on the same pre-training data, we see monotonic improvements. So it's not like the 7B models do not seem overtrained, but the 1B models are for the current, like whatever these almost checkpoints we evaluated on. And I think Joshua kind of like had this exact picture where early in pre-training we can think of, we are at a reasonable point, but like also most things are probably reasonable around there, and it's like it's just a flatter space. But after extended pre-training, we could be in the situation where you're locally at a really good loss, but everything around can be much worse. I don't think we have, I guess this is not surprising that people have had such intuitions about training models, but it's also like no reason why this has to happen. Like we don't have like a formal guarantee or like understanding for why the training dynamics kind of will have such a property. Yeah. Yes. Yeah, so that's exact control we did where no matter what our pre-training tokens were, we had the same learning rate schedule. So the entire learning rate schedule is the same across both.
Schedule, right? I mean, the schedules go down.
Yeah, sorry, but it's like, yes, it does go down, but like for every amount of pre-trained tokens, it ends up going down. So each of those checkpoints saw the same starting and final learning rate. And we had to do that because otherwise these models didn't, like language models were hard to train with a fixed learning rate.
But the pre-trained model already available and you can download it and do post-training.
Yes, so that's our first experiment. Yeah.
Maybe we need to reduce the post-training. We have over post-training. Do you think like?
I think the more data you use for post-training, you always see improvements because that's just like closer to the downstream task you care about. The issues in the pre-training.
I mean, as a developer, I download, for example, from Hugging Face a model to fine-tune my task. So what I will do, I have pre-trained model ready to use.
Yeah, I guess you need to think about which pre-trained model to use. Is maybe the claim. Like maybe you don't want a pre-trained model that has been trained too much.
Too much, yeah.
Yeah.
Which is good. If it's not trained too much, it means because pre-training takes a lot of time compared to post-training.
Yes, but yes, exactly. But it's good, but I think the current trend for improving capabilities is also to just like pre-train longer. So there's no clear answer here. Like there is an interesting sort of tension between trying to get models to be more capable, but also like kind of have them be adaptable in some way. Yeah. And so maybe the bigger thing is that we shouldn't be doing this two-step process of pre-training and then aligning, or if it's especially for high-stakes situations where we do want to make sure the model generalizes well. The inflection point depends on a bunch of things, the model size, but for a fixed model size, it depends on the magnitude of perturbation that we add. So for certain downstream tasks, at least in this Gaussian case, for smaller magnitudes, like you can pre-train longer and the model is still okay. But for higher magnitude perturbations, like this inflection point is smaller amount of tokens. So the point at which we start seeing detrimental effects really depends on how much perturbations we end up needing to add to the model. That was sort of the kind of takeaway here, which is that we kind of always see these very systematic trends. So in the earlier fine-tuning plots, we saw that in some cases we see an overtraining effect. In some cases, it keeps increasing. And we wanted to kind of get down to like, what are the trends that are consistent? And the trends that are consistent, at least in the Gaussian case, is that we always end up seeing these U kind of curves, but the point at which we start seeing the increase depends on the amount of perturbation we end up having to do to the model. And that ties back to kind of why we see this in some cases and not. So in general, like larger perturbation of magnitude that we need to add to the pre-trained model will lead to earlier onset of this overtraining behavior. So we'll see this increase sooner if we have to end up perturbing the model more. So back to fine-tuning or post-training. So we validate this assumption in some experiments, but we can think of fixed learning rate as a way of constraining how much we end up changing the model. We found that this worked a lot better than constraining in L2 or doing some kind of projections. And so we see a similar trend where for a fixed learning rate, we see this U curve. And as we kind of decrease the learning rate, it behaves like decreasing the size of the Gaussian perturbation you add to the model. So that's kind of the connection back to fine-tuning, is we can think of fixed magnitude of perturbation to be a fixed learning rate while we fine-tune these models. And now again, we see really clean systematic trends where depending on the magnitude of the learning rate, you see different points at which you start seeing the increase. And so it all comes back to hyperparameter tuning at the end of the day. So what we see is like smaller learning rate, if you can use it during fine-tuning, is great because it would lead to less forgetting and increased robustness. But smaller learning rate would also mean we don't end up updating the model too much. And so there is this tension where, at least with our current methodology, if we want to update models in some reasonable manner, we have this trade-off where if we update it if we want to change the model too much, we might also end up forgetting a lot more unintentionally. And so this trade-off between what ends up being the optimal learning rate really explains why we saw this overtraining effect in some cases and not in the others. So we kind of have this schematic where, so I call in distribution because that's the data set that we might do our hyperparameter tuning on. And so if it ends up being the case that larger models actually can also be updated less and still work well on in distribution data, then we don't see any degradation because the more capable model also requires less update. So it's good. But in many cases that might not be the case. And so if we end up needing to make a fixed amount of change across all the pre-trained models, then we see this very clear degradation because more pre-trained models cannot tolerate the same amount of change without forgetting. Okay, so you choose your hyperparameters based, you validate your learning rate on some distribution, but you could be measuring on like other distributions. So that's OOD. And so whatever learning rate you end up picking as like a measure of whether you've successfully adapted the model will tell you whether you've forgotten too much. So in cases where you could get away with updating the more trained model less, it's good because then you don't forget much either, and you'll see this trend where you kind of keep improving. But if you're in a situation for certain data sets where every model has to be updated with a large learning rate, then we see this degradation. So at least like the mental picture we kind of took away from this is that, so even though we see degradation in some cases versus not, there's actually sort of an underlying phenomenon that's universal here, which is that models are getting more brittle as we pre-train longer. And really like kind of whether this brittleness amounts to something in practice depends on what is the relationship between the pre-training and post-training procedures. How much do you actually want to update the model? And in some ways, updating the model more would also end up meaning that we degrade the model more, and that ends up meaning that our alignment or our fine-tuning process might not actually be quite robust.
Wouldn't you mix in pre-training data with fine-tuning data?
Yeah,
that mixture, is there some kind of system?
Yeah, we didn't run that. I imagine that it'll kind of put. I can't imagine that it'll solve the problem, but it might like allow you to find a slightly better trade-off. We could all, you could also try things like doing low rank updates. Maybe that finds a better trade-off. Yeah, and that's one of the things we've been experimenting in our group as well. Like, and I guess other people have also found like ensembling these models leads to a better trade-off, and ensembling the base and the fine-tuned model in some way. So there's definitely a large space of things that we could do that we haven't tried, but I think all of those will just find different points. I would be very surprised if something totally eliminates this trade-off completely, which would be great if there was.
Is the perturbation sensitivity related to the intrinsic dimension at all?
I don't have an answer that is beyond just a guess. Yeah, Yes.
I'm sorry to miss this, but can you say again what is mean distribution versus OD here?
Yeah, so in distribution is like kind of what's the data set that we're fine-tuning and picking our hyperparameters on. So you've collected some data, you're trying to see have you updated the model well, but in practice, we do want the model to work slightly beyond that validation set, and whether that happens or not is what we're measuring as OOD.
So now we're back to evaluating, not on like forgetting of the pre-training data. Now we're looking again.
Yeah, and I guess the loose connections, I think like whether the model is robust or not kind of depends on like the pre-train, like how much it retains its pre-train. Yeah. So yeah, what we find is extended pre-training can make post-training worse, which was but quite surprising because I think there's generally this question of like maybe more capable models also generalize better, and so it could be the case that that's true. And in some cases, it is the case where if we are in this world where the bigger the more pre-trained models also don't need are easier to adapt in some sense, they don't need to change much, then that could be the case. But in a lot of real world examples that we ran, at least this was not the world we are in, we actually end up seeing this kind of degradation where a model that has been pre-trained more is actually kind of harder to post-train in some reliable way. And at least our current fine-tuning approaches seem to destroy this pre-trained information. And you could argue that the Gaussian is maybe a very kind of loose abstraction, but in some way that's a way to model just changing stuff unintentionally in the model. And I think our current fine-tuning approaches do end up destroying this pre-trained information, especially because there are many tweaks to our current approaches that we can come up with that do slightly better, and maybe there's a whole space of things to explore there. Yeah, and the right regularization could in principle mitigate this, but we don't know what this is and if there even exists something like that. Sort of going back to safety in the last 5 minutes, so a lot of these experiments are actually kind of, they're not on safety specific data sets, but hopefully they kind of get us thinking about what are we doing right now with our trends of extending pre-training and what that means for post-training, since a lot of safety does rely on being able to post-train or align these models in this post hoc manner. And so there's at least some evidence that as models are pre-trained longer, like is a real possibility that it's harder to control via post hoc approaches. And kind of because of this ID versus OOD thing, we like whatever we end up tuning our hyperparameters on, like these downstream capabilities in some way, it seems like the degradation might be lower, or the inflection point might actually be like less for this compared to robustness, because really like we start seeing the forgetting more when we actually look at performance beyond like the data set that you're actually tuning on. And so we might not even see this degradation unless we're actually explicitly measuring robustness, which could be concerning because we really care about our safety training being robust because we want it to work even in kind of unusual circumstances. And broadly, more capable pre-trained models, at least our experiments tell us that they might end up being harder to align. And this was a point that was brought up earlier today, where it seems like it could go both ways. But there's like, at least with our current methodology, it might be, because we don't know how to post-train these models really well, we might end up being in the world where more capable models are actually harder to align. And I kind of wanted to bring back robustness into the picture because I feel like, to me, that still strikes as kind of the biggest challenge in our safety. Like, I guess there's the adversarial component for jailbreaking, but even if you're not being adversarial, like, do these models actually generalize to new grandma kind of situations or new ways of prompting these models or new agent setups? That remains like a really big question. And we should not take for granted that safety interventions will end up working well, or that just because a model is more capable, it has to generalize in some robust way. Well, hopefully this talk has convinced you that that's not something to take for granted. And I think that evaluations should really focus on robustness, and that's something that seems to be missing from some of kind of the discourse where people talk about different approaches and whether one works or not. But we need to be thinking about like which of these approaches generalize better, and that means we need to think about like what was the data sets that they were trained on, and it would be good to think about benchmarks as well as language to evaluate this kind of distribution shift and trying to really get at how much of these gains are just better red teaming data versus better regularization or better approaches to align these models for a fixed data set. And I think, yeah, that's basically the last slide, and happy to take questions. Thank you.
So I guess I have a question. So because you kept the model size the same, but increased the amount of training, I'm just curious did you ever look at like also scaling the model with it? Because I think like I get the sense that like as you train a model further and you get less and less loss, it's going to be harder to then do post-training. But if you have a model that's not trained to convergence or further from convergence, I suspect post-training to work better. So I'm curious, did you look at that at all? Or?
Yeah, so I guess on the control settings, if we ran a bigger model, everything just shifts to the right in some sense. So we can train on more tokens if we had a bigger model, but then eventually you'll see an increase. And so now the question is like, should we be scaling up the model size as we scale up the data set in some way? And that's a scaling law that we kind of didn't really look at, but that could be true, but that's also just a bit different from what people are currently doing. Yeah. Yes.
Back in 2021, like when we were thinking a lot about these distribution shift problems, there were also a variety of like distributionally robust optimization techniques to train models. What do you think about now bringing back some of those distributionally robust ideas, but for like alignment fine-tuning or safety fine-tuning, if that's the problem we're trying to solve?
Yeah, I think those would help. I also think that, like, to me, it feels like maybe the bigger leverage we'd get is from some kind of better regularization, and maybe things like, some of the stuff that you were talking about or other interpretability things. Can we bring that back to tell us how to fine tune these models in a way that's regularized? Because we're starting from a really rich starting point, and all of the DRO kind of stuff kind of assume that we didn't really know much about the world, and the only information was from our loss function. But I feel like maybe here there's a different space of approaches just because we have a better initialization. But I imagine that approaches like DRO should help too. Yeah.
Interesting thing.
So I do think that regulation is important, but it feels like most of the historical approaches there are trying to close train and test loss. And we could be in a bad situation where it's very fundamental that to get to low train and test loss, you need to find a sort of a narrow valley kind of thing. And so do you have like optimistic news to tell us about why we might not be in that kind of pessimistic world?
Because I guess I haven't run experiments in the safety data sets, so maybe that will help. But like we could be in this world where as models are trained more, like they just end up needing to be updated less too. Like there's something about our pre-training data or the process that just makes it easier to tell the model like what it means. Like like for example, you can just prompt the model in some ways and like everything magically sort of the model gets exactly what you want. So we could be in that world. I think it's unlikely, but that's we could be in the situation that we don't see this effect just because models that are trained longer don't have to be updated as much.
Thank you for the talk. Related to the previous question, the updates in a robust way, what about LoRa? In your experiments, you were doing, I think, adding Gaussian noise to all of the weights, or how about?
Yeah, in our experiments, we added Gaussian noise to all of the weights, and all our fine tuning was on all the parameters. We tried, we didn't try it comprehensively, but like some, initial experiments on LoRa felt like they were similar to fine tuning. At sometimes they kind of shifted the inflection point, but not always. So because even the LoRa process is like not necessarily regularized in the perfect way, so it still ends up adding noise to some subset of parameters, and so it just ends up like you can think of it as effectively a lower magnitude perturbation. So it just shifts everything to the right in terms of you now need to see more tokens before you see a degradation.
Could it be that early on during training, there are lots of circuits doing the same kind of thing, and then later on in training, they kind of specialize. And so there's one circuit for this thing, and if it breaks, you don't have any backups anywhere else. And that would put you in steeper valleys and also kind of make it harder to move things around. Is that?
Yeah, I think that's a reasonable interpretation. Like I haven't run any experiments into looking into these models and their circuits to kind of substantiate that, but I think that could be a picture of what's going on. Or in some sense, like, yeah, maybe if all the circuits are somewhat decorrelated in some way, then maybe like adding random stuff is okay. But like, yeah, like if they specialize or they end up being very, yeah, I guess if they specialize, it could be the case that, yeah, we have this problem. Yeah.
Take one last question then.
Sure. First, apologies for citing your own paper to you earlier. I didn't make the connection there. I'm a big fan of that paper. I have one remark and one question. One remark is that if you make these perturbations not as Gaussians, but perturbations that are highly probable in the posterior, this expected loss is what we call the learning coefficient. So I'll speak about that on Friday. So I'm very interested in that.
Yeah.
And the question was, could you go back to the last slide?
This one?
Yeah,
Okay.
sorry, it was a bit, could you repeat please, like what you mean by robustness exactly? And you mentioned generalization as well.
Yes, so sorry, I guess I ended up using robustness and generalization a bit interchangeably, because I think we can't even talk about like language models and distributions really, but so I think what concretely I was thinking about is like in our current settings, we don't have a sense of other models getting safer, or like are these approaches working better because the red teaming data is just kind of encompassing more things, or is it because these models are so capable that they are actually taking the same data but somehow kind of reliably behaving the way you want based on this data in other situations as well? Let's take the multilingual example. Like, is it the case that more capable, and I think this is a comment that was made in an earlier talk, that maybe models that are just better at processing multiple languages, like they can just be safer even if only trained in English. And I think this is saying that we don't have a way to answer those questions because we are not really looking at the red teaming data sets too carefully. Yeah.
Let's thank Aditi. Have a nice evening, everyone.